So after our discussion of atomic orbitals and generating electron configurations, the next logical step is to think about what this means for bonding. So I know I keep saying this, but again, we're going to kind of look at more information than you're really going to ultimately use during the organic chemistry course. But the goals that I have in telling you this information, one, to remind you what a bond really is. It's talking about overlap between orbitals. Two, I want you to understand what hybridization actually means rather than just calling something sp3. We want to understand what that means from the perspective of the orbitals. And then finally, we want to be able to talk about what double and triple bond really mean with regard to the orbitals that are involved. Okay, so we'll start here with a pretty simple model, just looking at how we might make the connection between H2 to form that molecule, or HCl, or Cl2. So this is a really simple picture, and the main idea that it's showing us here is as we bring our atoms together, whatever they may be, there is, in that initial connection between the atoms, what we call head-to-head overlap between the orbitals. So there's a lot of different ways to approach describing bonds, but that's where we'll start, to say the first interaction, the first connection between any two atoms is going to be a head-to-head overlap like we see here. If we want to generally speak about what's going on as atoms approach each other, this is a good model to talk about what's going on. Here we're talking about constructing the H2 molecule, and what we know is that if we observe the H2 molecule, the distance between the atoms is 0.74 angstroms, and angstrom is 10 to the minus 8 meters. That's a typical distance that we use to talk about what's going on with atomic distances. So what you're seeing here is the local minimum of energy. Essentially here what we've got is the optimal spacing between these two atoms. If we move them any closer, then the overlap would lead to repulsion, and then as you can see, the energy would go up drastically. And then in the other direction, as they move farther apart from each other, there's less opportunity for attractive forces, so the energy tails off gradually. So big spike when we push them too close together, and then gradually trailing off as we make the distance between them longer, which makes sense thinking about it as just a simple electrostatic interaction. So the key idea that we want to look at here is the concept of hybrid orbitals. So this is one of the approaches we can use to describe how orbitals are involved in chemical bonding. And for me, for organic chemistry, this approach with hybrid orbitals is the most convenient. So there's an issue that we have that may or may not be obvious at this point in time, and that is this. Our understanding of the electrons in our atoms of interest are that they are in s and p orbitals. And even if we describe it as the energies that we have, this is what we end up with. S orbitals and p orbitals like that. That would be the outermost, the valence orbitals for our carbon, nitrogen, oxygen, fluorine, the things that we're interested in talking about. So what we know is the geometries that we have can be tetrahedral or trigonal bipyramid or any of those sorts of things, but these pictures above are what the orbitals are. So the question to address is, how am I going to get like a tetrahedral geometry or a trigonal bipyramid geometry just by making connections using orbitals like this? And the answer to that is we are not going to do that. Instead, we're going to construct hybrid orbitals. So remember, these orbitals are coming from the wave functions describing the different energies of electrons in our atom. And the orbital pictures themselves are the square of those solutions, basically creating these volumes in space. But each one of these is essentially representing a wave function. So in the process of hybridization, what we're going to do is make identical orbitals on the valence level. So we're going to start here by looking at beryllium. Beryllium is 1s2, 2s2, 4 total electrons. And so technically the 2s2 is the valence level. And so if we were drawing a atomic dot diagram for this, we'd put the 2 electrons on beryllium like that. So there are really two things that we need to overcome. One is the valence orbital is doubly occupied, and we don't want that. We want 1 electron here and 1 electron there. So the first thing that we're going to do is promote one of our electrons out of the 2s and into the 2p. And we're going to pick the spin down electron because technically that one's a little bit higher in energy because it opposes the external magnetic field. So then as we follow that process, here's that spin down electron. Now we're going to scoot it up to the vacant 2p. And notice when we put it in, it'll be spin up because that's favored energetically. So now on the valence level, I've got 2 orbitals, each with 1 electron. But that's still a 2s orbital like that and a 2p orbital, like that. So that still doesn't really get us to the picture that we want. So that's where the process of hybridization is going to come in. So I'm going to take this 2s orbital and the occupied 2p orbital, and I'm essentially going to mix them together. Mathematically, it's taking the wave function that represents each of those and combining them together. And however many orbitals I combine together, however many atomic orbitals I combine together, that's how many hybrid atomic orbitals I'm going to end up with. So that's the next step in the process. So here is, I guess in this case, our 2s and 2px orbitals. I say x because that's the axis that we see there. And if we mix these together, we're going to get 2 new hybrid orbitals. And as you can see here, they're pointing at the x-axis, one in each direction, and we get the overall set of 2 orbitals, 2 hybrid orbitals, pointing to the left and to the right, and giving us the bond angle we expect for our linear geometry. So this example is not all that helpful because we could have rationalized this geometry just with the orbitals as they are, but this is the process that we're going to follow next for boron to get the trigonal planar geometry, and then after that for carbon to get the tetrahedral geometry. So if we had a molecule, for example, let's draw it out, like BeF2, and we want to talk about what's going on with this molecule, we would say that it's a linear geometry, both electron domain and molecular geometry, and the hybridization for it is sp hybridized. And so that's telling us that we mix together an s orbital and 1 p orbital to make these new hybrid orbitals. And we needed to mix together 2 orbitals because we wanted to have 2 electron domains around the beryllium. So that's what we're going to see. The number of electron domains we want our central atom to have, that's going to be reflected in the number of orbitals we're mixing together in the hybridization process. So again, I'm telling you more than we necessarily need to know, but I want you to understand when we say, for example, that beryllium is sp hybridized, what we actually mean there. So if we want to think about the picture of beryllium at this point, this is what it should look like. And if we want to make it closer to a typical energy diagram, oops, we don't need that one. Typical energy diagram, then it would look like this. Here's the 1s, here are the sp hybrids, and there are the unhybridized 2p. So as it is now, 1, 2, 3, 4. So we've got 2 singly occupied sp hybrid orbitals. That's how we get our linear geometry. So now, like I said, we'll follow that same process for boron and carbon. So with boron, 1s2, 2s2, 2p3. Oh, 2p1, sorry. I got ahead of myself. 2p1. So then those are our valence electrons, and that's consistent with the picture of boron we started with 3 electrons around the central boron atom. So then if we just look at what's going on in the valence, here's what it is, right? 2s2, 2p1. So remember, our first problem is we don't want any doubly occupied orbitals because we need singly occupied orbitals in order to form bonds. So the first thing we see is that spin down electron from the 2s becomes a spin up electron in what was then the vacant 2p. So then we take all three of these singly occupied orbitals, a 2s and two of the 2p's, and hybridize them to get three sp2 hybrid orbitals. So now what we're talking about is, let's say this 2s, this 2p, and this 2p, and we're mixing those together. So it's 1 part S, 2 part P. So these are going to be sp2 hybrid orbitals, like you see here. So visually, what does that look like? Well, again, it's kind of hard to draw this math out, but if we want to try to do that, that's sort of what we would say that it looks like. So we're mixing together the 2s with the 2px because those orbitals are on the x-axis, and the 2py because those orbitals are on the y-axis. And if we combine together the wave functions that represent each of these atomic orbitals to go through the hybridization process, what we end up with is the geometry that we would expect, which is 3 orbitals pointing at the corners of a triangle to give us this trigonal planar arrangement. So I know it's kind of hard to visualize how this happens without considering the math behind it. What I try to do as I look at it here is just sort of think, if we added these shapes together to get a new combined shape from all of those, what would they look like? And that can sort of help us to understand how we get this, this diagram. And of course, that math is beyond the scope of what we want to talk about, so I'm just kind of showing you the pictures that describe the math behind it. Okay, so hopefully it's making sense, the steps that we're following here, right? Make all the orbitals we're interested in singly occupied, and then mix them all together to get hybrid orbitals. The name of those hybrid orbitals will be based on which atomic orbitals we combine together. So with carbon, now we're talking about 1s2, 2s2, 2p2. So we're looking at 4 valence electrons, right? Typically, if we were thinking about carbon and drawing the atomic electron configuration, it would look like that. So to begin with, right, we've got the doubly occupied 2s, and then 2 of the 2p's are singly occupied. So same thing, we only want singly occupied orbitals, so I'll take that spin down electron and move it to the vacant 2p. Notice it goes in as a spin up. Then we'll take the 2s and the 3 2p orbitals. Now we're going to hybridize them all to get sp3 hybrid orbitals. So same thing, make them singly occupied, then mix them together to reflect the number of domains you want around your central atom, and that's how we get sp3. Here, visualizing gets even trickier because we're thinking in 3 dimensions. Right now it's the s, the px on the x-axis, py on the y-axis, pz on the z-axis, and this hybridization process now ends up with 4 hybrid orbitals pointing at the corners of a tetrahedron. And so that's what we see. Let me scoot down a little bit. That's what we see down here. So that's how that geometry forms. That mostly covers what we're worried about with regard to hybridization, but while we're here, we'll quickly acknowledge what happens when we go beyond the octet. That'll remind us of how third row elements can have more than 4 electron domains. They just have to use d orbitals in order to do that. So that's what we see when we talk about stuff like phosphorus and sulfur. So I think this example is for phosphorus, which would be, if we're doing the shorthand electron configuration, right? Neon, core, 3s2, 3p3. So what we immediately see is we promote that electron. So now there's a singly occupied, oh, let me go back for 1 second, sorry, we went up. So this spin down electron in the 3s becomes this spin up electron in the 3d. So since it's in the third row, we're able to access d orbitals, but now we get what we want, which is 5 singly occupied orbitals. But in this case, the singly occupied orbitals, it's an s, 3 different p orbitals, and a d orbital. So these new hybrid orbitals are going to be called sp3d. If we do the same process for that we did in terms of getting the shape out, well, now we've mixed in a d orbital, which remember kind of looks like a double p orbital. So now the hybrid orbitals all together start to look a little bit more like d orbitals, but it does give us the trigonal bipyramidal geometry. If we keep going to the final step of this, we would get, with something like sulfur, then we'd get an s orbital, 3 p orbitals, and 2 d orbitals, and that would give us sp3d2 hybridization. Okay, so what do we want to do with all of that information ultimately? Well, now we want to be able to, when we look at a Lewis structure, not only talk about the electron domain and molecular geometry, we also want to be able to talk about the hybridization. So the important thing to know is whenever we're thinking about this, it's electron domain geometry that's going with the hybridization. So in order to figure out the hybridization, you want to look at the electron domain geometry, not the molecular geometry. So if we look at diagrams like we had before, or slides like we had before, where we started with the Lewis structure of CH4 like that, now not only can we talk about the electron domain and molecular geometries, we can also talk about the hybridization. I don't remember if we talked about the polarity part on these types or not, but I think we did. It's completely symmetric, so it's not polar. What about where there is a non-bonding pair on the central atom and we want to do the same process? Well, remember, it's electron domain geometry that's dictating the hybridization. So tetrahedral means 4 domains or 4 orbitals. So it's sp3 because we mix together an s orbital with 3 p orbitals. So that's how we're able to determine what the hybridization is. So again, in addition to knowing the electron domain and molecular geometries, now I want you to be able to tell me the hybridization as well. Is this molecule polar? Yes, because it's asymmetric, right? It's trigonal pyramid. It's a non-parent geometry, so usually that ends up making it polar. And of course, there are some exceptions, but that's typically the case. Okay, so then the last thing that we want to talk about as we're into hybridization and thinking about orbital overlap for making bonds is what it really means when we talk about a double bond or a triple bond. It's not the same overlap happening additional times. It turns out the second connection or the third connection between atoms is going to happen in a different way. So we want to make a distinction between sigma bonds and pi bonds. So whenever you see sigma bond, you should be thinking single bond. And more correctly, we should say the first interaction between any two atomic orbitals or any two orbitals to make a chemical bond, that's always going to be a sigma bond. So if your molecule only has single bonds, those are all also sigma bonds. So what do we mean when we talk about a sigma bond? The real thing that we're trying to say here is that it involves head-to-head overlap. So we bring the orbitals together along the bonding axis, and they overlap to some extent. That's what we mean by a sigma bond. And then if we think about what that really means in terms of the overall picture, it means there's cylindrical symmetry of the electron density along the internuclear axis. So what does that mean? That means if I'm thinking about, for example, H2, then the electron density shared between these two atoms is filling in that space literally between the two atoms, and it's symmetric about the bonding line. So if we continued the bonding axis through the molecule, it'd be symmetric through there. That's what it means by cylindrical symmetry of electron density about the internuclear axis. So then what's the other option? If there's not head-to-head overlap, what else is possible? Pi bond is talking about what's happening with the p orbitals. So pi is coming from what's going on to form these. It's the interaction of unhybridized p orbitals. So that's why it's called a pi bond. So rather than head-to-head overlap, now we're talking about side-to-side overlap. And I think this will make more sense as we look at some structures, but they're not overlapping head-to-head, traveling along the same axis. Instead, they're both perpendicular to that axis, but we bring them close enough together so there's some amount of overlap. And then with regard to the electron density, it's going to be above and below the internuclear axis like we see here. So if there are additional connections between atoms, any additional connection is going to be classified as a pi bond, and it will occur through p orbital overlap. Like I said, I think that'll make more sense when we look at a picture. So single bond's pretty clear, right? If we just make H2, there's one connection between the atoms, and that's it. If there are multiple bonds, like I was saying, count the first connection as a sigma bond and the second connection as a pi bond. So in this case, CH sigma, CH sigma, CH sigma, oops, that was more of a delta, CH sigma, CH sigma, and then CC, count one of those as a sigma and one of those as a pi. In a triple bond, that's going to make it sigma, pi, pi. So any additional connection between the two atoms is going to be a pi bond. So that's just a rule to learn, and usually in general chemistry, that's about as far as we get. We just say count them like this. But what does it look like in terms of the picture of orbital overlap, and how can we make sense of it? Well, how about a molecule here like formaldehyde, where if we're counting, right, it's sigma, 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 pi. What's really happening with the pi bond? Well, think about what's happening with this carbon. This carbon is sp2 hybridized, right? There are 3 electron domains, so we need 3 orbitals to do that. So sp2 hybridized. Well, what that means is I've got my, switch colors here. I've got my 3 hybrid sp2 orbitals, but that means there's an unhybridized 2p orbital. And for carbon, that one's going to have an electron in it. So 4 valence electrons, but if I only want to make 3 connections, 3 electron domains, I should say, then that 4th one is just going to be sitting in the unhybridized 2p orbital. So it's really that electron in the 2p orbital that's going to end up forming the pi bond with oxygen. So if we look at the diagram here, all this in red or pink above and below the plane of the molecule, that's the pi bond, showing perpendicular overlap of those p orbitals between the carbon and the oxygen to make that pi bond, whereas everything else is sigma, right? CH, CH there. So that's what the pi bond is. It's the interaction of the unhybridized 2p orbital with whatever other element, whatever other p orbital there is. For the oxygen, it's also got 3 electron domains, so it's sp2 hybridized, and that oxygen has a spare singly occupied 2p orbital as well, so that allows for the interaction. How would that work for a triple bond then? Well, if we're looking at a triple bond, then our carbon electron configuration, it'll be 2 sp orbitals and 2 unhybridized 2p orbitals. All of them are going to be singly occupied. That's carbon, right? 4 valence electrons. So for each of the pi bonds, we're going to use one of these 2p electrons. And so imagine one is in the 2p y, let's say, and the other is in the 2p z. So in each case, we'll get our own pi bond. So it's a little hard to interpret what's going on in this picture. Let's see if I can help a little bit. I don't know if I can or not. This orbital and this orbital are above and below the CH molecule, whereas, oh, sorry, that's all one orbital. This orbital here, that's the one that's in front and behind the carbon. And so these guys are matched up to make a pi bond. and then these guys are matched up to make a pi bond. So overall, those are the p orbitals, right? It's double lobes, but they're interacting with each other across the molecule, not head-to-head, but side-to-side overlap. So each one of those overlaps is representing a pi bond. So for this Lewis structure, right, we would say, oops, let me finish the Lewis structure. We would say sigma, 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 pi, pi, right? The triple bond, one of the connections is sigma, the other two are pi. So that's what we want to be able to do as we describe this process. So hopefully that's making okay sense. So then how about a molecule that we might encounter in organic chemistry and trying to think about how we would describe this? So we're going to look at some simple molecules containing 2 carbons, and we want to talk about what's happening with regard to the hybridization and also with regard to sigma and pi bonds. So this is what the molecule C2H6 looks like. And so when it's symmetric like this, we can just pick one carbon or the other in order to talk about things like electron domain and molecular geometries. So if you're using the AB classification, we'd call this AB4, which would lead us to say that the electron domain geometry is tetrahedral and the molecular geometry is tetrahedral. We want to be able to say, since the electron domain geometry is tetrahedral, it needs 4 orbitals, so it's going to be sp3 hybridized, right? An s orbital plus 3 p orbitals. So that's what we would do to describe C2H6. So imagine from here that I take away 1 hydrogen from each of the carbons and make a pi bond between them. That's what we'll look at next. So now rather than C2H6, I'll make C2H4. If we look at the molecule, the valences are met, right? Each of the hydrogens has a formal charge of 0. The carbons each have a formal charge of 0 as well. And if we're counting, it would be sigma, 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 and then the double bond is 1 sigma and 1 pi. So when we follow the procedure here, right, we'd call this AB3, which means both the electron domain and molecular geometries are trigonal planar. And what's happening is the unhybridized 2p orbital from each of those carbons, they're overlapping with each other in order to make the pi bond. So if we think about the electron configuration for the carbon, it's going to be, rather than 2s, 2p like this, it's going to be sp2, 1, 2, 3, and then an unhybridized 2p, but all of them are going to be singly occupied. So we would have started from here, move the spin down from the 2s into the vacant 2p, then mix the 3 orbitals together, leaving that 2p available for forming the pi bond. Okay, then lastly, what about C2H2? Well, now we took away 1 hydrogen from each carbon again, and so now we have a triple bond between them. So if we're labeling, right, CH sigma, CC sigma, and then pi, pi. So if we look at the carbon, it's got 2 electron domains, so that's why we would know to say AB2 geometry, linear electron domain, linear molecular. And then if I look at the orbitals, so same thing, we would have started same way, 2s, 2p, and it's still carbon, so it would be 1, 2, 3, 4. Now, since I only need 2 electron domains, I'll mix together the 2s and the 2p, and then leave the other 2p's undisturbed. Since I mix together an s and a p, I get sp hybrids, singly occupied, and then the 2p singly occupied as well. So the SPs are being used to make the sigma bonds, and the 2p unhybridized are being used to make the pi bond. Okay, so as I said a few times, right, this is kind of excessive in terms of going over electron domain geometry, hybridization, etc. But I want it to make sense to you as we go forward rather than to just memorize what the hybridization is. Okay, so I think that's it for chapter 1 stuff. I think we're ready to get into chapter 2 when we get back to class. So I'll go ahead and stop here.